Very nice. Thanks for staying with us. I want to make one remark before I start, since it came up a few times now regarding the presence or not of stochastic maps, quantum channels in what I've been describing. So in the original plan, you can still see it in the old versions of the slides. The third chapter was about quantum channels. There is in fact quantum channels in this article, quantum monadology. It rests on the fact that there is actually yet another monad. You know, there's an important monad in stateful computation called the state monad, the famous thing in computer science. It goes, if you have a state space H, classically, it's the monad that takes the product with H and then the Hom, the internal Hom, out of H into that. This is a monad from classical types, have an H, classical types, or on classical types. And one observes that in the quantum context, the same construction kind of applies, but if H is dualizable, so quantumly, this is just a something about quantumly, so if this becomes now a finite dimensional Hilbert space, then of course homing into it, the same thing as tensoring with H star. So now we have a monad that tensors with this is BH, right? This is bounded since we're finite dimensional. This is all linear operators on H. So this is how the algebras come in, and then one can now play the monad game again and see what all the units and co-units means and so forth, and find that this knows about quantum channels. So there is a chapter on quantum channels in the quantum monadology. And originally I thought I'd talk about this, but then I changed my plan. Just wanted to mention this.
So you're using the H dual. This is already like the internal hum, right?
Yeah, exactly. Yeah, in like on the linear or type system. So it's not like So it turns into this on the quantum types. And then one can just unwind things. So I think that there should actually be a close connection to what we've seen in the other lecture, even though I haven't actually worked on making that connection. But I think anybody who feels energetic about it can probably find some fruitful exercises there. Just wanted to mention this. Right, so what we were talking about, so this was more quantum language, and then I decided to do more of the homotopy aspect of it. So let's recall what we did. Homotopy quantum data. So I had this lightning review of group words, and then I switched gears and we talked about physics. And today I want to kind of proceed in the same manner. We first talk about group words again, and then I come back again to the physics, and we see that there's a curious incarnation of this stuff. So this is some. So I want to talk about symmetries versus evolutions. This is a topic that came up last time, I think, a few times already. We've seen that a dependent quantum type that depends on a group point of classical worlds somehow is equipped with transformation groups, with quantum transformations that form groups. And we've already touched informally, I think, on the fact that these actions can mean two things. These group actions on a quantum state can be symmetries, as in gauge symmetries, or they can be evolutions, as in Schrödinger evolution. It's also a unitary operator, or any quantum gates, right? We've seen the Clifford group in a talk yesterday. That's called a group for a reason, because it's a group of quantum transformations that are not regarded as symmetries, that are regarded as things you actually do on a system that have physical meaning. So I want to make here a general abstract observation about how to disentangle these things, and then we see that this actually very neatly fits in both with the quantum language of quantum measurement, and then actually with the physical application, where we distinguish asymptotic symmetries from bulk symmetries. So the setup is here, as it says. Maybe let's see, I'll do some things on the slides, and then maybe some computations you can do on the board, depending on how it goes. Maybe it works well if I just point it. So our setup is a normal subgroup. That's important. H and G. And last time, so I call this inclusion I. And just to stick to the previous notation, maybe I can scroll up just once more to remind us. So previously we just observed that these categories of group word representations, and I still haven't fixed this type. Oh, there was one. I knew one more was missing. Yeah, I fixed two, and there was another one. Okay, so there was the observation that for every group point, we have a category of its group word representations, and they again form a Grothendieck motivic yoga or a dependent type system, whatever you want to call it. In particular, they have these for every functor, for every map between group words F, this is a joint triple of functions going back and forth, pull back and push forward. We're going to be concerned with these two here. For the moment, actually just with the pullback. Observe that the pullback operation is what the typo-written expression here is saying. It's just a pre-composition. The representation itself is just a functor from the group point to category of vector spaces, and pullback, as it's called, or restricted representations of F as a monomorphism is just a pre-composition of them. And so let's look at this situation again for the case that we have a subgroup inclusion, H into I, and then we remember for each group, we can consider the corresponding looping group point, just a group with a single object and that group as automorphisms. And the F, the generic F, just to have a shorter name for it, take to the BI. So it's just the map from BH to BG, which sends the single object to the single object as it has to, and sends the homomorphisms, the morphisms here, sort of to the image under I, what they are. And so we consider now a G representation, so representation of the larger group. So a map here from the functor from BG to the category of vector spaces, big bullet. And recall that the F star, as I just said before, is just this pre-composition here. So that's the setup we're dealing with. And here's the first observation now. For every, if we have that, so if we have a choice of such a G representation, then its restricted representation actually gives rise to controlled quantum gates in this homotopical sense now, as follows. I claim that in this bundle notation, every element in the group gives us a map from these dependent quantum types to these dependent quantum types, which on the basis is, I'll talk about this maybe just in a second in a bit more detail, but from every automorphism of groups, we can deloop it to a map between the delooping group points. And here we take the automorphism that is the adjoint action of G on H by conjugation. So it's actually an outer in general, not necessarily inner automorphism here, because G may be from the larger group G. It's conjugation in the larger group. And so the observation is that every such map here, which kind of changes the notion of how the symmetries act, is actually covered by a map HG. So this bullet notation is not meant to be, see, this is a functor. And in here, we insert what is being evaluated on. So this is supposed to be very neatly matching our previous notation. We remember H bullet, as we had a dependent quantum state over a set, was such that the fiber, right, if I restrict it here to, if I pick here a little w in here, then the fiber over this is HW, H little w, right? And so now that we have a groupoid, so as this now becomes promoted to a groupoid, I allow there to be morphisms here, H transformations between these elements, and then I have an HW prime, and then my clever notation is such that, you know, the H now also knows how to evaluate on gamma. So H gamma is the linear map. The linear map from this vector space. So it's just a kind of suggestive, hopefully, notation for functors. And that's what I'm using here in these bullets. So this will appear, you'll see it appear here. Okay, so this is now a good exercise actually to just think about how this category of homotopy dependent quantum data that I just called the Groton deconstruction last time actually works in practice. So let's think about what does it actually mean to build such a morphism. And so remember, this is a morphism in the Groton deconstruction. So the intuition is, and that's what the Groton deconstruction makes precise, that if we have a map to somewhere, we can actually pull this back here along the map here to make this live over this VH. And then we can just look at a morphism of H representations here for the same H. Right? So this picture is actually notation for this picture in terms of, this is kind of the total spaces, and that's the classifying maps. So on the left here, this is the classifying map for this thing. So here we're claiming, or it's not claiming, it's here we're denoting our restricted representation of H. Well, it's being a representation, it's some functor from BH to vector spaces, which has this name, right? That is this representation. And now we need a morphism to sort of the same guy pulled back along this map. But pull back, remember, so pre-composition. So from this functor, we go to this composite. This is pre-composition with the adjoint action. and then comes the representation. So our morphism here is really now a morphism in this category of representations between these two representations that are both now defined over here. So it's some natural transformation filling this diagram. I just have to work out what this means. So this is now a natural transformation, two functors on BH. Here's a generic morphism of BH from point to the point, labeled by some H. Here's the image under this functor. Well, it sends the point to a Hilbert space at there's a single Hilbert space really here on which stuff is represented, or vector space. And here's the functor, the actual linear map H evaluated H. Whereas here on the target, the codomain is the precomposition with the adjoint action. So that's our Hilbert space evaluated not on H itself, but on its image under the adjoint edge. Right? And now the claim is, the observation is, well, can we fit some natural transformation here? So can we assign to the point a linear map that makes this diagram commute? But evidently we can, since H is a restricted representation. We know that G also exists, even if G is not an H, but it was a restricted representation. There is a G action. So we can put the value of HG here, and then you see by the nature of the representation, this commutes, right? This composite is just, it kills this G inverse, right? Composition is in the opposite order. So this composite is HGH, and this composite is HGH. So this commutes. So thereby we've defined this natural transformation, so that thereby we've defined this morphism. So we've built a quantum gate, which for states that do have something that is going to be the symmetries acting, there's still something now that acts non-trivially, and with the stuff that comes kind of from outside, from a larger group G. And notice that what happens down here, it's a sort of thing which might be hard to, to guess if you didn't have a formalism of group points here, because there's a single world here, if you will, and there's a single world here, so somehow the world doesn't change. It's just that the symmetries get conjugated. There's a subtle slight change in perspective of the symmetries. In our picture, in the physics picture, that single world is essentially, it's related to what shows one of these surfaces on which we're evaluating the surface that we're looking at, and this changes how we look at its diffeomorphism group. Anyway, let's come to this. So that is first observation. We get quantum gates this way. And now let's just think a bit closer, a bit more about what these quantum gates do. Because remember or observe that I allow G, little g, to be in G, but it might just be in H, right? Because H is a subgroup of G. So am I saying now that every element in H gives actually an operation which kind of goes against the idea that I already mentioned, that I want to think, we'll see in a moment, that the H does actually play the role of the symmetries. Well, it does. I mean, certainly the claim here, the construction works for any H and H, but we'll see now that it's actually pure gauge then in the following sense. So let's just look a bit about what are the transformations of BH. So what comes now this year is sort of independent of the rest of the discussion. It's just a little exercise in groupoid theory, a basic fact of groupoid theory. So what is called often called the automorphism 2 group of a group H is the automorphism groupoid of its delooping BH. So, which I mean it's the automorphism object in the 2,1 category of groupoids. And what it just means is this. We're in this category of groupoids where you have maps, morphism of groupoids, with homotopies between them. And so for any object, we can form the groupoid, as it were, whose objects are the automaps, the invertible maps, and whose morphisms are the homotopies, the natural transformation, right? And our claim, this groupoid, these objects, these morphisms, these objects, is the action groupoid, remember the quotient groupoid of the automorphism group of H by the inner automorphisms of H, acting by the adjoint action. You know this exercise, but let me just show it here as the diagram, so it's clear by functoriality that an invertible map from BH to BH, where it has to take the elements of H to themselves in a manner that respects compositions. So it's a group homomorphism. It being invertible means it's a group isomorphism. So it's clear that the alpha and alpha prime are automorphisms. And so what's the natural transformation between them? Well, for any morphism, it needs to make this, so it's some morphism here that makes this diagram commute. So but this means its component, its unique component, is just an element in H, now called eta star. It's the value of our natural transformation on the single object. And see again by commutativity, like kind of going from here backwards down there. This is alpha H combined with a joint action, alpha combined with the conjugation by eta, and the diagram says it has to be alpha prime. So this says that alpha and alpha prime are related by composing with an inner automorphism. So that's exactly what this action groupoid does. So, but right, and just as a side remark, this groupoid now has its own group structure in the category in the groupoids, and that's why it's called a two-groupoid. Just like you can compose these things or something, but we're actually not going to use it. So in particular now, it means that the inner H automorphisms, I mean, that's just another way of saying this really, the inner H automorphisms, they loop to homotopy trivial BH automorphisms. Right, as a special case of this, if, I should maybe put a B here for consistency, I realize now. So if we now consider the situation where one of our automorphisms is already inner, well, then it's actually equivalent to the identity by the automorphism that just conjugates with the inverse of H inverse. So we see now, remember up here, that we said we have these operations for all elements in G, but we see now if the element is actually in H, then this operation, at least classically, is actually trivial up to gauge. Gauge, it's pure gauge. And the same is actually true for the full operation. You can now see that in that case, actually the full operation is gauge trivial. So here's the triangle, is the previous triangle that was the triangular incarnation of our quantum gate. Remember up there, the quantum gate was this kind of morphism in the slice category of mod C. And of course, these morphisms, I haven't really said this in formal detail, but it's kind of clear. They themselves have automorphisms, kind of these tin can diagrams or paper cup diagrams, as they're called, where we can change the top morphism here by a homotopy, if there's a compatible homotopy in the back. But you see, by what we just said, the top morphism is now gauge equivalent to the identity. And composing this is a little exercise in thinking about composing natural transformations. This H cancels this H inverse, so that this actually becomes the identity transformation. So what this is saying is that if our H is actually in the subgroup H, then these quantum gates, these controlled quantum gates that I observed exist, are actually homotopy trivial, they're pure gauge. They're not actually there up to gauge.
So what is one way, I mean, would it make sense to say that if you think of as the groupoid that parameterizes your types as some sort of like labeling of the classical parameters that you use to control the system, is this saying that you could change the labels in a way that is not physically, it's pure gauge, no, in the sense that you're not implementing any physical operation there beyond just changing the labels. Is this
yeah,
a way to think about this, or
yeah, it sort of sounds to go in the right direction, but let's just sort this out. So there's now we have labels as we had before. Worlds W prime. These were different labels already, like measurement outcomes. But in addition now, if we pass to the skeleton, they have some sort of automorphisms. There's some gauge symmetries here that don't actually change the world, but it's still operate on it. And we're now saying we're not currently. I'm just looking at the case where there's just a single world, because it generalizes easily to disjoint union of more worlds, and just asking what happens to these symmetries, right? But yeah, I mean, with that understood, so if you grant that these are also kind of new labels now, these are like two labels, and these were one labels, right? These are higher labels, then yeah, then it says something like this. It says, how do we want to say it? I mean, it says what it says, right? It says there's a Hilbert space or a bunch of, or a vector space that has an action of a symmetry, so that knows that certain operations transform it into itself. And there's also actual operations on this Hilbert space that turn it into something different that are physically observable. And I'm arguing that I'm giving a proof for why some of these operations that look like they're physical are actually part of the gauge transformation. So in the physics system that I introduced last time, and I'll come to this in a moment, there was the H will be gauge transformations of this gauge field we looked at together with diffeomorphisms, so kind of gauge and gravity symmetries in the bulk at least. And what I'm working towards is to understand that even though we're in a generally covariant system, some of the symmetries, and the asymptotic boundary symmetries, will actually act as actual physical operations, evolution. Okay. So that was observation 2. And so the lesson so far is that we're just putting this together. We see that for quantum state spaces that are of this form, that are restricted representations for normal subgroup inclusion, the G transforms, transformations of the kind I just introduced, they decompose into two things. There's the symmetries that are those labeled in H, and the evolution is kind of the rest. And the rest means in this group language, it's the coset, right? So if I take any element here and evolve with it, well, the H component of it has is pure gauge. So whatever remains is in the coset. So since we're assuming a normal subgroup, the cosets form themselves a group. And so we get the short exact sequence of possibly non-abelian groups, where these are all transformations that we are kind of given by, from the physics picture, this comes from, it comes from somewhere. That's all what we have, like in the construction that I will come back to in a moment, comes from forming these moduli spaces and see what internal symmetries they have and how diffeomorphisms act on them. And then there's a subgroup and there's the evolution. And that's kind of cute because you might say, well, but why are we looking at state spaces that are restricted representations? But now observe that these are exactly the kind of state spaces that our language predicts are the ones that support quantum measurement. Remember, that was actually the starting point in the first two lectures. There the map F. So now we have this. So now our F was this somewhat more subtle gauge thing where we have a single world for the moment, and our F was this BI here, but it plays the analogous role of what previously was here was a set of worlds, and here was a point actually, or maybe gamma. I call it sometimes a set of background labels. And this was P or something. And right, so these play the same kind of roles. In this case, let me not call it P. Let's keep calling it F. In this case, we saw that the quantum states are given by finding kind of finding a quantum state here, which is the state space to which we collapse once we measure it, which I always assumed in the first two lectures to be just the one-dimensional space. But you could also choose this. A measurement doesn't have to single out a one-dimensional subspace. It can single out a larger dimensional subspace. And now that we have symmetries, it will single out some irreps of the symmetry. So that with that understood, remember that our quantum states were really the push forwards of the unit bundles here in W, which are the pullbacks of the line here. So in the previous, we saw that the quantum states actually were formed by this necessity operator, which pushed the things forward and then pulled them back. Where this pushing forward was the thing that summed up the labels. And then we're restricted. And so we can do the same thing here. The abstract formalism tells us if we still call these our quantum states, then we will have a measurement process given again by the co-unit of this operator, and will satisfy again all the properties that you expect of quantum measurement, such as the deferred measurement principle, because they depend just on the fact that this is a co-monad and nothing else. So this says that this is a good context for understanding this. And now let's go back to the physics. So remember, we were talking about, just briefly to recap, we're looking at gauge systems where I was looking at the topological sector using the fact that what's called flux quantized gauge systems have a classifying space that classifies their topological excitations, the topological sectors of the fluxes. And then we recalled what the classic classifying spaces are, BU1 for electromagnetism, and we observed that for certain low temperature quantum systems, these things apparently are no longer classified by the ordinary BU1, but it just fell from the sky, and the way I presented it, we just checked that if you replace that classifying space with S2, then it begins to see exactly the kind of structures that one sees in the laboratory that happens in these systems. In particular, let's see. So in particular, let's talk about this. So I last time I glossed over this, but I want to start talking about this now because we want to talk about this idea of the onion. So the idea is that in some of these fractional quantum Hall systems or other potential topologically ordered materials, as it's called, there should be some kind of things. The literature keeps being a bit vague about what it is. They first introduce them as generalizations of fermions, but then they become quasi-particles. So there's some kind of particles, well, as you can see here, that are expected to have this property that when they interchange positions, when they pass by each other, that some phase is being picked up, either the phase or its inverse. So that processes like this, where particles move around each other by braiding, are actually detectable by a global phase that kind of affects the whole quantum system. And the idea of this topological, or the broad idea, very broad idea of topological quantum computing is that since these phases are dependent only on the topology or the linking form of this link here, as it were, and not on how this path here wiggles around, that it's a robust observable, and if you can kind of cleverly enough arrange for, computing a certain number that you're interested in as a combination of such phases, then you could in principle implement effective quantum computation. And I just want to mention for what follows now that this two-sphere classifying space that we saw sees the correct spaces of states of the binary Chern-Simons theory, which is supposed to be the effective field theory characterizing this on closed oriented surfaces, also sees, in fact, this braiding for what you might call the solitonic excitation. So do I have this picture here? Right. So the idea is that in our material, which is some kind of surface, there's the magnetic flux forms localized, so-called Rikursov vortices. It's localized in certain patches, which are really the images of the pre-images of the Pontryagin theorem when they're all mapped to the two-sphere. And it's that these flux quanta that kind of bind in some not really deeply understood way to the electrons to form the quasi-particles that are supposed to have this funny braiding statistics here. And so just to amplify, because we will kind of need this in following, just to amplify that this two-sphere coefficient also knows about these braidings, we can work out what is the remember our quantum observables was pi1 of the mapping space from our surface into the two-sphere. And now let's actually do this for the most trivial case where we're actually in R2, we're on R2, but since we're looking at what's called solitons, since we're looking at the regular but localized topological configurations of this flux, we constrain the flux to vanish at infinity. Our laboratory ends somewhere, it's not infinite. And so this flux business has to happen in a finite region, it may not escape and run away. And mathematically, this is nicely reflected by forming the one-point compactification of whatever surface we have. We add the point at infinity formally to the system, which, right, so R2 doesn't have an infinity, but we can kind of say, well, everything that runs off gets at infinity, and so adding this just makes R2 the two-sphere. This is a standard trick in instanton theory. And then one looks at the pointed maps to S2. These being pointed means, well, the S2 itself, even though it's of course homogeneous, but it has, we can choose any base point here and say, well, the map that goes to there is the trivial soliton configuration. Doesn't matter which point we choose because they're all the same. One of them, I mean, we could just regard this S2 also as being of this form and call this new point 0. And so having pointed maps then encode to whatever classifying space we have, encodes exactly the soliton condition that our fields at infinity, literally now, at the point, take the point at infinity to 0. And so we ask, what are the quantum observers then on R2 on our such defined solitonic field configurations? So that means, for what I just said, that we're looking at pi1 of the pointed maps from S2 to S2. This first S2 being really our R2, the laboratory, idealized, this sheet of material we have with a point of infinity added. And then again, by some yoga, well, pi1 of this is pi0, as we saw maybe already last time, of the loop space of this. One can bring this in by using smash product closure. And this is the same thing as maps from S3 to S2, which again is classified by the Hopf vibration. And now, the interesting thing is that this mapping space here itself, I already mentioned the Pointarian map, I went ahead of myself there. This mapping space itself is canonically identified very nicely with exactly the kind of configurations of flux quanta that you want to see. Maybe I'm being a bit quick about this one here. But let me draw it to the board here. This is the Pointarian theorem, sort of under the hood. Before it was called the Pointarian-Thom theorem. Before Thom came in, already 15 years earlier, Pointarian had this unstable version where we have some manifold here, M, and you're mapping it to a two-sphere, to a sphere of some dimension, but I'm just going to draw the one sphere here. So this is an Sn, if I may, and I regard it as being an Rn with this point at infinity added here. And so if you have a sub, so this is a manifold. If you have a submanifold here, which has what's called a normal framing, so that it's the vicinity of a tubular neighborhood is identified with the trivialization of the normal bundle, so that you have a global notion of what it means for a point to have some normal distance to this manifold. Globally within some neighborhood. And then what we can do is we say, well, if the point is close enough to the manifold, we send the point. So right, we can identify every such transverse thing here. If the manifold has codimension n, we can identify it with a copy of Rn and send this point here to its corresponding position here in the Rn, sending everything that goes out of the neighborhood to infinity. Sorry, I'm not saying it very clearly, but maybe you get the intuition. So this is how for the normally framed submanifold, you get a classical homotopy, a map to the sphere. And conversely, if you have a map to the sphere, a transversality theorem says you could always choose it to be smooth, such that 0 becomes a regular value, so that if you take the pre-image of 0, which in the correct construction the other way around was the locus of the manifold, so the pre-image of 0 is a manifold, smooth manifold, and so that any small neighborhood of 0 here gives the pre-image the normal framing. So using this kind of, this is Pointarian's old theorem, and then Siegel, much later, so this was in the 1930s, and Siegel in end of the 1970s maybe, he generalized this to, at least in a special case, to observe. So this gives a bijection between, so it should say, covariance classes of such manifolds and homotopy classes of such maps. So it gives an identification at the level of equivalence classes. Siegel's theorem refines this to the actual full space of maps. So it's, in the particular case that we need it here, it says that the pointed maps from R2 with this point at infinity added to S2, where a single map, what is a single map? By this Pointarian theorem, a single map is a bunch of codimension two manifolds with normal framing in R2. What is this? This is just a bunch of points. These are the codimension 2 submanifolds, right? And the normal framing is just a sign now, whether or not the little disk sort of around the point is oriented in one way or another. So this should be, by Pointarian's theorem, you expect this to be this kind of what's called a configuration space of points in R2, where a point in the space is a configuration of points, and a continuous path is a movement of these points around each other. There is a subtlety though the idea is correct. One just has to be careful with the right topology of this space, because so you kind of naively expect this to be a configuration space of points in R2, going like this, with signs, signed configuration space. The points have signs, and it should be such that if a positively signed point, which is kind of a flux quantum of some positive magnetic flux unit, can annihilate with one of negative unit. But it turns out if you do a naive formalization of this, where the elements are actually points with the signs, these are the plus point and minus point, the process where they merge and annihilate, you want to say this is a continuous path in this configuration space. You can form such a topological space with such a topology that turns out to be not quite have this homotopy type. It comes close, but it fails. And it took a while, until just, I think maybe 10 years ago, that Okuyama figured out the way to solve this is to thicken the points to strings, interestingly enough, even though it's a bit of a coincidence here, which have charged endpoints, where we now have configurations of little intervals, and they made the continuous path in the configuration space of these points may now be such that the endpoints annihilate the way you would expect. Once these strings merge and form processes like this. So a continuous path in this what's called the Okuyama configuration space of intervals as objects configurations of such strings where continuous processes are those where the endpoints can annihilate. So this gives a minor correction to the topology of this space, which is why these processes that I've already shown here have this thickened form that I'm showing you. So this is actually a loop in the configuration space of these charged strings. So it's actually a loop in the mapping space. Remember, we're interested in the loops in the pointer mapping space from S2 to S2. And with all these people, Pendragon, Siegel, and then Okuyama, I should say, working on this, we find that a point in this loop space, which is actually identifiable with a framed link, namely just some kind of picture like this, a link where the link has this thickening, which gives it a framing. And then we can work out what is the class of these as we pass to homotopy classes. So what Pendragon would call the covariant classes of these. Well, we know that pi0 of this space is pi3 of S2. So we know the integers that come out, and the little computation shows, so this is from our article on abelian onions and phi frames, little computation shows that the number that a framed link is sent to under this identification is exactly its linking plus its framing number, just the total crossing number, in fact. So it's the number of times essentially that different components of the links intersect with each other. There's a factor of 1/2, some conventions in there, but it's essentially that number. The framing number is kind of the number of times that a link twists around in itself, being a thickened thing like this. The interesting thing being that this is exactly, linking plus framing number, is exactly the classical result that this so-called abelian Chern-Simons theory is meant to have as quantum observables. The quantum observables of abelian Chern-Simons theory are supposed to be what's called Wilson loops, so just links. And the story there was that originally people wrote down, I've tried to understand these things with the path integral, which of course isn't properly well defined, and then one gets an expression for the invariant which actually diverges, and then this framing is introduced as a way to regularize or cancel the anomaly. But once it's introduced, these are the regularized anomaly cancelled Chern-Simons observables. They just drop out in the correct form right away here from the algebraic topology. So I want to say this because it's important for what comes next. So this was like one further check that this classifying space S2, CP1, knows about the physics that is expected, or that has been seen in these one process. And now, let's just generalize this a bit. So the issue here is that these solitons that we now derived exist somewhere in the system. They somehow have these phases. They somehow behave in some form. They are realizations, in this case, just rigorously mathematical realizations of this idea of having quasi-particles that kind of pick up a phase when they cross each other. But the problem is that, which as far as I can see, has not really found attention much in the literature, is that you cannot compute on these things because you cannot grab them. There are somewhat there, and there's a couple of articles that claim to have seen them or have seen signatures of them being present. But in order to do a computation, right, you need to control your system. You need to grab it and tell it, move it through some process to have it produce an output. But this is not the case here. There was no way to produce these things. So we're going to go towards a way to actually have what's called defect onions, to actually have externally parametrized objects in our material that we can actually move, or can at least imagine that we could move by some external processes. So that movement by the adiabatic theorem produces some transformation on the ground state of our quantum material. And since we now have a candidate classifying space for the theory, we are in a good position that we can now, so we check that it reproduces previously known or expected phenomena, or we can just keep computing because now the thing is completely well defined. And so we can just compute what it predicts for new situations that have not actually been considered, as far as I'm aware, in standard Lagrangian Chern-Simons theory. And we can ask the following question: what if our surface has literal defects in the sense of punctures? That the surface that I kept talking about, the oriented surface of genus G, has actually some points removed, which, if we pass to the point compactification again of these surfaces, since removing a point, which is a closed submanifold, makes the surface have another end, and the one-point compactification identifies all the ends of the surfaces with a single point at infinity. So going all the way to the infinity of R2 now becomes the same as going very close to any of these points that we have removed. Both of them are no longer in the surface. So doing that and still mapping to S2 means now that, because this is a pointed map, it makes the flux avoid the points that we've put at infinity. The solitonic nature of flux is that it doesn't go to infinity, right? And so the physical meaning, we're just doing this mathematically now, but the physical meaning would be do something to the material that expels the magnetic field from certain regions. So one can think about how to do this. This would be the characteristic property of type 1 superconductors. Maybe I can do something else. But let's imagine we have this and let's see what follows. Well, then we can just compute again our algebra of observers. So it's the same thing. Pi1 of the mapping space from our domain into the classifying space. Now we just need to understand what this new thing is. It's the one-point compactification of this n-punctured surface. And there's a little exercise here for this page 11 of Hatcher, very classical construction, which tells us how to compute this. Let's do it for two punctures. So here's our one-point compactified R2, but with two punctures. So this is S2, funny notation for S2. We have two punctures. And let's consider adding an arc, gluing an arc to our sphere here, where these punctures are. Then the standard fact, this is a CW complex, which has these two arcs here, which has this one-dimensional subcomplex. And the standard fact of algebraic topology says that if you have a CW pair, as it's called, then if you shrink away, identify with a point a contractible subcomplex, then that process produces your homotopy equivalent object. So contracting away this new arc A here, what does it do? It shrinks this away, so it makes these 2 points coincide with the new point here. This is this adding of a point at infinity that I'm actually defining, that I'm actually looking at. This is the pinched sphere here, where the 2 punctures are now at infinity. But I can just as well contract this arc here, which is the arc that was already there. It's inside the sphere. And that gives me manifestly, that just makes the outer arc remain, but its endpoints join here. So this becomes what's called the wedge sum of the sphere with the circle. You can easily see from this argument now, if you have more punctures, you just get more wedges of a circle here, as shown here. So in general, this one-point compactification of the n-punctured sphere, or in general of any surface actually, is just the wedge sum of the unpunctured surface with n-1 circles, one for each puncture except the first one. But the wedge sum is the coproduct in pointed spaces. So mapping out of this in pointed spaces just gives us the product of the corresponding mapping spaces. But we know these already. The first factor here gives pi1 of maps from the unpunctured surface, and the others gives us pi1 of maps from each circle to S2, which is again pi0 of maps from smashing the circle of S1 to S2. So it's pi0 of maps from S2 to S2, so it's a bunch of copies of Z. So in particular, if we started with the surface, we see that these solitonic observables now are n copies of Z, which is like the n-fold result of the observables that we had for the one punctured surface, where we saw this copy of Z was this, when it acts on a state, it gave us a phase. It was the braiding phase of the stuff braiding around. So somehow, in a way that I admittedly have trouble to visualize, but I don't have to because I just proved it. Somehow for each puncture now, in the vicinity of each puncture, there's one phase for how the onions braid there, That phase may change as we move from one puncture to the other. So that's again the solid tonic observables, and again you see it's just a bunch of phases that we pick up. Abelian phases, one says, so it's not unitary operator, it's just complex numbers. But then we saw last time already that we should really think of this as a generally covariant system, and that these observables are not covariantized yet. They actually need to be acted on by the diffeomorphism group of our punctured surface. And on the diffeomorphism group of a punctured surface, by some abstract results, orientation preserving is again actually equivalent to the homomorphism. So we can again replace the smooth maps by homeos, taking pi 0 of this. And a famous fact of mapping class group theory says that sort of this group of large gauge transformations, of large diffeo transformations, what's called the ordinary mapping class group of G. This is the one we already talked about last time, that acts on the standard Chern-Simons states on a genus G surface. But it's now extended by what's called the surface break group. And that is the group indicated here of motions of these defect points around each other, right? Such a diffeomorphism can send the n-punctured sphere, say, to itself. But all the points are sitting at the same infinity, so it can shuffle these points around. They should move them around in such a way that it forms braids. So, I mean, it's kind of intuitively obvious, of course, when there's something to be proven, but these are very classical facts of topology. And this is being the surface braid group means it's these kind of processes, but possibly in a non-trivial surface. So these braids might move around some non-contractible cycle in our surface. But if you're on the sphere, it's just kind of this group that is shown here. And this is the kind of group, that is exactly the group that one expects in topological quantum computation to use to implement quantum gates. So the idea would be if now a system is acted on, a quantum system, is acted on by these braids, well, then it forms what's called a braid representation, a linear representation of the braid group. And so the idea then is that for each braid that you specify, you get a unitary operator acting on your system. And now if you want to compute some unitary operator, it being the quantum circuit you want to compute, what you have to do is find a braid, possibly a huge braid, whose associated unitary is at least close to the one that you want. That is the idea of topological quantum computing. And the idea is it involves critically like if we talk about implementing this practically, you critically need to be able to kind of grab these defects and actually move them. It's not sufficient to just know that something is just zipping around in your material. You need to, in a controlled way, produce this thing. Called the quantum adiabatic theorem, right? You have some system whose Hamiltonian depends on parameters being the positions of these defects. And as you slowly vary these parameters, your system transforms by the quantum adiabatic theorem, remains in the ground set if it was in the ground set before, but it may pick up some unitary transformation. So that is the idea. But what I want to highlight now is that the way we set it up, we see that these homeos, they seem to arise as gauge symmetries, right? They were motivated here as the gravitational, if you will, as the generally covariant symmetries of this topological field theory, Chern-Simons. So I want to address, and finally come back to the original motivation I gave in the first lecture. I want to address the question of, since none of this has actually been realized in the lab, and since things that have been realized seem rather dubious, or claims that have been made seem rather dubious, it's maybe worth checking again foundations of what can actually be realized. So I want to think about what part of this symmetry group can actually act as evolution instead of just symmetry.
Yes. So just so that I understand, if you were to realize something that has this mathematical property, you would need a material that has the property that the defects sort of repel the flux, and that you can also control them.
Yes. Okay. And as I just said, I'm far from being an engineer or something, but it doesn't seem out of the question because the materials that expel magnetic fields are known. They're called type 1 superconductors. So if you can maybe dope your material, whatever it's called, right, make these little defects where the semiconductor at this spot becomes a type 1 superconductor, right? If you just speak hypothetically, it doesn't seem out of the question that this can do. Or something like that.
And so you're sort of working backwards, right? That you start from the mathematical requirements of your system, and then you would think, what sort of physical implementation can I find in this?
So in the broader context, when this is material from another kind of angle where where we say, look, these strongly coupled systems are not actually well understood. The people go and say they should be described by this Lagrangian theory, but there's actually internal contradictions when you describe fractional Hall systems in terms of what's called the effective Chern-Simons theory. The Chern-Simons Lagrangian that people write down, and they know it, actually violates flux quantization. It violates the Dirac charge quantization condition because it kind of builds, it tries to build in the fractional charge. I haven't really talked about this, the fractional charge that these quasi-particles want to have, but then promotes the quasi-particle charge to what's called a statistical gauge field. And then it doesn't make sense anymore, actually. And you can see it even Witten has lectures on topological systems where he just openly admits this. He says, look, this was a fun derivation, but that's actually a problem, but let's just move on. It's also in Tong's lectures, is the same comment. So these are, I think, intrinsic problems, which are not too surprising because global effects of flux quantization are inherently not visible properly in the Lagrangian formulation. The Lagrangian formulation, you want to write down something like involving dA, which involves the gauge potential. So you're explicitly already on a chart, on a single chart, and explicitly are not seeing the global situation. And what we're doing here is we're saying, well, let's try to find a better theory of this that is non-Lagrangian, actually, where we use the fact that we know we can compute the observables on fluxes from some other means, observe that they just depend, the topological ones, just on the classifying space, and then we can just change the classifying space. That is the assumption. So we say, look, we have a new theory that produces topological quantum observables just from the input of a choice of classifying space. So if you have a classifying space, as it always goes in physics, right, that matches known observations, then everything else it implies is a new prediction. And here I'm saying, if we make this assumption that S2 is the correct classifying space for these fractional quantum Hall system, then it predicts rigorously. There's just no, it's a simple computation. It's just no way around it. It predicts that if you can engineer these defects somehow, they will have quantum observables forming the group algebra of this thing here. Yes. And then I want to go even one step further. So first we had this and we were quite fond. We said, okay, it's great. It's exactly what everybody wants. But then, I don't know, I started thinking about what I was doing. I thought, isn't it strange that I'm saying that gauge diffeos are now observable? So somehow there was, in the success, there was a little worry here. So that's what I want to come to now. Then maybe we, how much time? 30 minutes left? And now I just want to, since I think it's really fun. Oh yeah, sorry, I should have shown this before. So this is the picture that people have. This is my picture, but this is the picture that people have about topological quantum computing. I have some quantum state here for some positions, and you kind of manage to break them around somehow by doing something to the system, and you enact a unitary operation. So let's say here, but okay, that's all what I just said before. Let me just say again. So since the break group arises here as a group of gauge symmetries, and maybe general covariance, will one actually be able to use it as physical evolution? This is really a special case of the general question that we mentioned a few times. These groupoids reps that we're talking about, abstractly, irrespective now of fractional quantum Hall system, they represent the encode operator actions, which a priori can be both symmetries as well as evolutions. So how to disentangle these? Well, we actually saw how we could start going about disentangling them at the beginning of this talk. So if we choose a normal subgroup and declare that this is the actual symmetries as opposed to the rest. But where does this arise in physics? Well, this is actually a well-known phenomenon, it turns out. It's called asymptotic symmetries, which on spacetimes has boundaries, specifically with the asymptotic boundaries. Notably on just Minkowski spacetime, it is well known, it's a classic effect from the 60s, I think, that just gravity on what's called asymptotically flat spacetimes, such as spacetimes that have a black hole somewhere, but otherwise nothing, and asymptotically become flat. The diffeomorphisms they have, which leave the boundary, the asymptotic boundary fixed, so which decay in a suitable sense towards the boundary, they are actually gauge symmetries as it should be in gravity because they're diffeomorphisms. But those diffeomorphisms, which actually, one has to say this properly, which act on the boundary, on the asymptotic boundary, like translated in time, they can actually be observed. This goes originally by the name ADM mass. Arnold Misner observed that for asymptotically flat spacetimes, you can actually define total mass of your given gravitational system, kind of all the stuff that is inside, that is away from the asymptotic boundary, and then it evolves by some ordinary temporal evolution equation for an asymptotic time that is actually defined. This was later than defined the BMS group and other things. It has become a topic of its own. This is here Strominger's lectures on soft theorems, which are all about this stuff. And this article was just posted, this is by Postma just a couple of days back, which maybe gives the best account yet of the most precise, mathematically reasonable account of these things. But the situation is always this. You have some system that has diffeomorphisms or even generally gauge symmetries. And some of them act trivially on, in some sense, on the boundary or on the asymptotic boundary, bulk diffeomorphisms, and they are supposed to serve as the actual symmetries. Whereas the rest, which is again the coset, the quotient, so it should be a normal subgroup. People are a bit shy about admitting that. There's some people who, upon one article of people who said, well, what if it isn't? Then they call the coset a non-invertible symmetry, which I think is something you shouldn't do. But anyway, so in good situations, it is a normal subgroup. And so you get the quotient group, which is then the group of actual physical evolutions. This is kind of the stuff that, these are the symmetries that act non-trivially on the boundary. So let's just see if something like this can play a role here. Well, let's look at boundaries. Let's look at surfaces that have boundaries. So I used, without really explaining it much, this notation that should maybe admit it. So this was my notation for oriented two-dimensional manifolds, surfaces closed. And then I had here G was the genus, so the number of topological holes in it. Then N was the punctures, the points that are removed, the defect anions for me, or the complement of closed subsets, that's important here. And then lastly one, I mean, this is a very classical thing, of course, going back to the ancients, to Gauss or something, is one can add boundaries. One can allow the surface to have boundaries. And now what I want to do is focus on the simplest case, focus on, just as a test case, let's consider the annulus, the punctured annulus, the N punctured annulus. So this would be sigma 2. So annulus, I get it from singular sphere, so it's genus 0. Then I want these N punctures, and I say it has two boundary components. So it's just this thing, this surface that is the interior, right? With punctures. Here's a puncture, here's a puncture. Aha, okay. So maybe I should use some other color. Not so important. So these are boundaries. These are actually part of the, this is important for the one-time configuration. These are actually part of the surface, the closed boundaries, if you will. And then we remove punctures here. It's N. Which we think of being our anions. And these things have actually been discussed. I mean, this is the topology that has actually a reasonable chance, or that has been implemented in the laboratory. Everything that looks like a disk is easy to implement in the laboratory. Like people like to talk about putting these systems on a torus, but this is not really realistic. It's quite, I mean, people have very sophisticated arguments for how you could have a system that effectively looks like a torus without being one. But this is a setup that actually can be realized in the lab. You just take out this material in the middle, you have this thing here. So, okay, so what is it? So there's a standard, there's a theory of these things, mapping class groups of pointed theorems. So here's a reference, which you could look at if you like. So it says, it's the following, the mapping class group, remember this is our group of would-be, it's a group of diffeomorphisms, so would-be symmetries, mapping class group of the N-punctured annulus. It's an extension, it has two kind of free generators. And so the form is always, right, as we saw before, I think I mentioned it before. These things are always extensions of some simpler mapping class groups without punctures by the corresponding braid group. The fine braid group is really the group of, as is essentially shown here. Well, I'm not quite sure. It's the group of braids where the braids are not, where the points are not, as in my previous slides, sort of sitting in a line, but where the last one can break to the first one. It's just this F here. And these are two generators. This is the one called tau traditionally. That is the one that kind of is present in the plane annulus. If you don't have any punctures, then the only element in this mapping class group is the operation which kind of twists it. It fixes this boundary. It becomes the one turning around move of the outer boundary, and it interpolates it in between. So it takes the annulus and kind of twists it once around itself. That is tau. That is sort of the actual diffeomorphism of just the underlying annulus, whereas these two things have to do with the punctures. And this is interesting. So this rho is the thing that moves our points one step around the annulus. So if you think of, as we may for these purposes, right, everything is up to homotopy. So for every question, you can always, with some care, try to kind of first bring it into a configuration that suits your problem. So let's arrange them in equal angles, and then you can just look at this braid that just rotates it one step with this clock here. And it's interesting. You would think, well, wait a second. Well, what does this have to do with boundaries now? Well, the same operation exists on the disk. If you fill this in here, you can also, there's also this diffeo that twists these things around. But there, you can, it's actually, because we're looking at pi, the mapping class group is pi 0 of the diffeomorphism. There turns out on the disk, this diffeomorphism is actually connected continuously to the identity. But it's not connected, so this unwinding that exists on the disk has to act in the middle. You have to have the diffeomorphism of the whole annulus. So it turns out that once you fix the boundary here, that unwinding no longer exists. So in this sense, this operation is a boundary effect. It appears, up to topology, we can't really quite see, are we at the boundary or not? We have to see, does the diffeomorphism that we're looking at, does it or does it not fix the boundary? And so this one wouldn't, and so it's not there. And so that's an interesting, that's a new element that we get. And so the statement would then be, it's just another incarnation of that same. So by what we said at the beginning of today's talk, it means now that we get controlled quantum gates, of which there's more plausibility that they're actually physically implementable, right? So I'm just, if you recall what we said at the beginning, we're exactly in this situation now. We have a normal subgroup, and we have something in the quotient. So this thing is actually the semi-direct product of these two things. Maybe I should have said this. So we're exactly in the situation where our normal subgroup of symmetries is this plane break group, which is the break group you would see on the disk. So if there were no boundaries. So it's manifestly, in this sense, the bulk part of the symmetries that is unaffected.
On the puncture disk, no?
On the puncture disk, yeah. If we have punctures on the disk, yes, that's what I mean. But without if you don't have this in a boundary. So this is manifestly the bulk symmetries. Everything is equivalent under this. But now we can find, well, okay, we have to choose a representation of this. And once we've chosen this, we put it back and so forth, and get this operation here. In fact, you could not just use any row here, as we said before. This can be row composed, so it can be the cyclic movement composed with any other braid, which would all be in the same coset. So which of these you actually be able to realize in the lab, which representative in the coset will depend, I suppose. But that's it. And then I didn't quite find time to say the punchline now, which I really wanted to say is, but this then also gives you an idea of how to measure these things. Because now you want to say, include the break group here into the full mapping class group and look at the necessity modality that is induced by pushing forward along that and pulling back. And the co-unit of that adjunction, that should be the measurement process that theory would predict is available for these boundary observables, the system, right? So we have here the break group, the bulk symmetries is there appears to us now, but it sits inside. So this is our BI, which was our F. It sits inside B of the full mapping class group. In fact, of the full, in addition to the mapping class group, there is these maybe further factors of Z coming from the gauge symmetries of R. Right, so the full symmetry, remember, was here, right? So the full symmetry is the actual mapping space with its internal gauge symmetries proportionate by the diffeomorphic group. So I'm not writing this down right now. So this would be the bulk diffuse, bulk supported diffuse. This would be MCG here of sigma 2, 0, and V. This would be the nominal, say, nominal diffuse, all the ones that you have that you can use, and then associated with this is now on our quantum states, right? So here's mod C is the parameterized quantum states of, let me write VMCG simply, and here's mod C B breakthrough. So there's this induced junction here, F lower star and F upper star. And this induces a monad here. We did before the necessity monad, F. And so the statement would be that, right, the language predicts that if you measure something, then you're using the, no, I shouldn't do this here. If you measure something, then you're acting the co-unit of this thing. Here's some V, just as we had before. This is the state collapse. And all the previous discussion applies, but now it will kind of tell you what you have a right to expect to actually observe for such topological systems. That's what I wanted to say, and I did. And I guess there's 50 minutes left, but maybe let's stop here and see if there's any questions.